right, we're good to go. All right, guys, we're going to start the next talk. Thanks for coming about understanding modular blockchain infrastructure with EVM. Looking forward to it. Just remember, if you want to speak with any questions during the FAQ, I'll come over with a microphone, and we need to talk into this for the streaming. All right? So go ahead.
All right, sounds good. Hey everyone. Today I kind of want to talk to you guys about basically things about how to get into the EVM, what the modular blockchain infrastructure currently stands as, and kind of delve deeper into what it entails for the entire ecosystem. Paper is not working. Super. Just to introduce myself, I'm QEDK. I do smart contract engineering at Polygon. Prior to this, I was in India alumni. I was part of the Here India Fellowship. And before that, actually, for a while, I was also with Moonshot. I was one of the founding engineers there, which is the version to get pointed out. That's mostly about me. Let's talk about EVM, right? Let's talk about the agenda. Alright, so basically what we'll be covering today is what exactly is the EVM? When we say the words EVM, like what does that really mean? We'll go into a bit of like what is the blockchain trilemma, what we seek to solve, where we'll be in the next couple of years, why we sort of need modular blockchains. We sort of want to establish that there is a need for modular blockchains. That's what we were building towards. And delve into the current solutions that we have today, the solutions that we have in the future, the solutions that have been in the past. And finally, just to insert an idea, basically the idea of sovereign rollups and how it kind of can change the view of modern infrastructure in the next 1 or 2 years. So with that, let's talk about the EVM virtual machine, right? So basically, if you look at the overview, or like if you have a very basic understanding what the EVM is, it's basically a giant global distributed state machine. So basically, we will come to the state machine part later. Basically, we kind of think of it as there being a world state, which is basically this large data structure that stores like all the accounts, the balances, the nonce, and some particular code that decides to address. And basically, you have the idea that with each block, there are these set of rules that are defined in EVM. The idea is that the block transition can only happen when those particular preset rules are followed. And this can be any sort of code, right? You can put in arbitrary code on the chain, and then it will execute according to those set of rules. And that's basically what the EVM seeks to do. And so basically, the way you can kind of look at EVM is it's essentially a specification of rules to follow. We'll come to the implementations of it later, but basically, any set of machine instructions that follows those instructions can be called the EVM, so to say. So if you look at this diagram, courtesy of EVM, we basically understand like there's this persistent world state that is basically persistent between transactions to transactions. This is what we refer to by having the large data structure that we talk about, which is basically a very large multiple tree, shall try to be specific. There is some storage that is persistent. There is immutable code. Basically, any address that is stored is technically immutable. You can kind of think of it as a virtual ROM. And then finally, we have the volatile machine state, which is basically that persists from one transaction to another and is not persistent between them. Where we basically have like the stack that processes those instructions, and we have memory, which is like another transient part of EVM that will come later on. So basically, if you talk about the EVM specification, it's basically a stack machine which has a depth of 1020 bytes. So it basically means that you can stack up to 1020 items. Obviously, this is not feasible for most applications, which is why what you do is you take the items often on the stack by storing it from memory. And each of these are basically 256-bit words, which was primarily chosen because they are very useful useful for 256-bit cryptography. So basically, what Ethereum is built on, which is basically CAT. They kind of account for that is the reason of using 56-bit words. Now, Vitalik has actually come out and said like maybe there is not a great choice because like you're using a lot of computation, and in most cases you will not need that much amount of storage for most of the calculations. But it has an EVM specification detail anyway, which is very useful. Also for the Bitcoin, for example, like SECP 256K1, but again that's not really applicable to Ethereum, so to say. So we mentioned memory in the previous slide, but what we're basically referring to is that between transactions you have the option of using a transient memory, which is basically an word at rest byte array. So if you look at Solidity code, you might see downloads and mstores, which is basically like you're reading from very specific parts of the array and you're taking it off and on the stack so as not to overload like the 1024 limit. And finally, we come to the storage part, which is basically the multiple structure I was referring to earlier, which is again a word addressable word array, so to say. You can basically kind of think of it as a giant mapping from a Geth perspective, or technically it's still a multiple structure, right? But basically, there's a storage slot. The storage slot has some accompanying data with it, and that should be stored. And this is again stored in the global state as part of something called a storage root. We'll kind of describe this more with diagrams and data things. Right. Let me just find the correct one. Yeah. Right. So basically, what is a transaction? So a transaction is sort of the most fundamental part of the EVM, so to say, because basically what each transaction is it's a state transition function. So basically, like let's say if you were to send 1 Ether to the person next to you right now, right? So basically what would happen is it would trigger a transaction from EOA, you would sign that particular transaction with a signature, it would be sent to an RPC, it would validate that the signature and the public key that was used to send with it matches, and you would treat that as a valid transaction. But basically, the way that you can kind of imagine it to be is that you have a pre-state sort of pre-world state, which is like S, and you have applied state transition function Y to it to the transaction T, such that you get a new world state after it, which is basically S naught. And so the way you kind of need to think of it is that transactions are sort of these atomic actions that are applied on top of the previous world state, and they either go through or they do not. So if they revert, basically means you go back to the previous world state, which is basically like nothing happens to it, and if they're successful, it means that you have kind of induced a change in the world state, and that is what you refer to by the state transition function. So yeah, basically if you look at this diagram again, courtesy of Ethereum.org, you basically understand like how Solidity kind of implements this. Like if you want to implement from a Solidity perspective, you basically have these program counter gas available. You have some immutable code that is on the address. So let's say like you're calling a contract where all it does is just deposits some Ether, and that's all you do with it basically. So it would basically execute the code with whatever call data you have passed. Typically what happens is you are giving a function selector, so which is basically like a 4 bytes signature of whatever function you want to execute. It executes a jump instruction to that particular function, and it executes that function with the particular call data that you provided. That is how Solidity works. Other languages might execute it differently. And then within that particular transaction execution, you have the idea of stack, memory, and storage. So again, stack is basically, as I said, the most fundamental part of the EVM, since EVM is technically a stack machine. You have the memory, which is the transient memory that exists between transactions, and then the storage. So basically, anytime that you want to read from storage, you can load it onto stack. Anytime you want to read from memory or vice versa, you load it onto the stack and then do those operations. So as you can see from this diagram, the operations only happen on the stack. That is basically the idea of EVM. Since it is an EVM, it's a stack-based machine, the operations of the instructions can happen only on the stack, which means that you can kind of interact with memory and restore it back to memory. You can interact with the storage, restore it back to the storage, and then do this particular transaction. And finally, obviously, we also have message calls, which is basically if you were, as an EOA, if you were to send a transaction, imagine a contract doing that for you, basically. It's executing that same code on some particular different address, so to say. And that's kind of treated as a message call. And then it's kind of another flow of this entire stack, memory, and storage. You can kind of think of it as like that. And so that's basically what transactions. You can kind of think of them as simple state machines. And finally, we come to talking about smart contracts. So when we talk about smart contracts, what we typically understand is that it's just code that is being executed. It's a code that is stored at some particular address, and that is being executed when you invoke some particular code on it, which is called the call data. So a very simplistic idea of a smart contract is a program that resides on the blockchain. So it has some logic, you give it some data, it spits out the output, either it reverts or it doesn't. And but what makes EVM special is that EVM doesn't distinguish smart contracts from externally owned accounts, which is basically like the wallets that you make on MetaMask, right, which have private keys. From an EVM perspective, an EOA is exactly the same as a smart contract, with one fundamental distinction, which is that a smart contract cannot send transactions, which means that every transaction needs to be initiated by an externally owned account. That is because smart contracts, since they are treated to not have a private key, they cannot sign those transactions, they cannot prove to an RPC that they have ownership of the private key, which is why there is that fundamental distinction. But in all other scenarios, they are basically treated the same. If you were to make a call database transaction to some Uniswap v3 contract, it would be exactly the same as if another contract did it. And that is what makes EVM so special, because then you have this entire ecosystem of EOAs, and you have this entire ecosystem of smart contracts that kind of interface and build off each other without actually caring whether you don't need to care if it's a smart contract or an EOA. It just works, and that's what's special about the EVM. We spoke about Ethereum storage earlier. What we should also talk about is basically like the 4 different kind of tries that are basically existing in the EVM. So the most important of which is basically the world state try, since that is responsible for storing your account state, which has like nonce, balance, storage root, and the code hash. So again, when I refer to code being stored at an address, actually only the code hash is stored, which is basically like get jack 256 of the particular code that you have deployed on the chain. And then you have basically the storage root. So basically when we refer to some code residing at a storage slot for a particular address, what basically happens is it's sort of like this byte address, word array, and you make a Merkle Patricia try out of that, you get a root node, and then you commit it in the storage root for that particular account state, which in turn, again, we produce a Merkle Patricia tree out of, and then we have a root node, which is the world state try, which then gets committed in a block as the state root. Then we have the transactions try, which is also important because the transaction you provide, the transaction data needs to be stored somewhere to ensure data availability. We'll come to this kind of later on. So basically, transaction has some certain properties related to signatures like VRS and other details, for example, related to like nonce, so you can't replay them, so on and so forth. You become Merkle Patricia out of that. You get a transactions try that becomes a transaction root that again becomes part of the block header, and the same with the receipts try. Receipts try is basically after you execute a transaction, you get a transaction receipt, which basically includes like the logs bloom, the logs, any off-chain computation that you want to do. For example, if you are running an indexer service, you will rely on the receipts try to provide that basic data for you, so you can kind of index them and build off other services or the centralized or decentralized services that you want off on top of that, which then gets committed to a receipts root, and which is again part of the block header. And so this is basically the fundamental part of the EVM, and this is also sort of the bottleneck of the EVM, so to say, because you have the 16 leaf tries, and technically, since we do not have history expiry or state expiry, again we'll come to this later on, what it basically means that the chain is growing at scalable, like unscalable pace, so to say, which means that we need ways to scale this later on. And we'll also talk about how modular blockchains can help with this. So the first idea that I want to introduce here is basically what is the execution layer. So basically, if today you were to send a transaction, you'd basically just be signing some data, you'd be sending it to the RPC, the RPC would be sending it to some node, and they would basically, what they would do is they would execute those transactions, they would ensure that it is valid or invalid, and they would, it would either succeed or fail, right? We kind of can, the way the Ethereum layer on works is that it kind of tries to combine all of those roles into one chain. But theoretically, what you could do with modular blockchain is kind of split the components off into separate parts. And so we can technically have an execution layer that doesn't do consensus or data availability, so like a rollup. So let's say if you were to use Arbitrum today or ZK Sync today, the data availability is still reliant on Ethereum L1, but theoretically the execution is happening only on the Arbitrum or ZK Sync chain, and which basically means that you've already taken one task off the main chain, which basically means the Ethereum nodes don't have to care about that particular execution task anymore. And so that is what the idea of an execution layer in a modular blockchain world kind of translates into. Then we come to the consensus layer. You can kind of think of it as the DA layer as well. But what it basically means is that you have a layer that is responsible for validating the blocks, ordering them, and then ensuring that there is consensus to include those particular blocks. So with context of the current state of Ethereum, we basically have the idea of execution clients and consensus clients. So basically what execution clients are responsible for currently is basically taking those blocks in and executing them. And then it's actually the consensus clients, which is like Prism and Teku, which are responsible for, which have their own separate peer-to-peer network, which has a completely different specification compared to an execution client like Geth or Aragon. And they basically participate in their own gossip layer, where they are receiving these new blocks from peers, and they're broadcasting them when it's their turn to be the when it's their turn to be the block proposer. But yeah, similar to the execution layer, there is also the additional task of a discovery protocol. So you can kind of coordinate with other clients, you can assert consensus, you can ensure that the chain can move forward. And we'll talk about how kind of this ties in with the current state of modular blockchains as well, so to say. So yeah, so this is basically just a short note about the merge and what it kind of entails for us. But basically, before the merge, there used to be a beacon chain. I mean, there still is, but now the beacon chain is actually producing normal blocks. So from an end user perspective, what was basically happening is you would have these empty blocks, which have some state root, which have some parent root, a prev random, and some other fields. But what they wouldn't typically have is the actual execution payload. So what happened with the merge is we basically started taking those execution payloads from the execution layer, and then we started including them in the beacon chain blocks. So what that basically means is now the validators on the consensus layer are validating that those execution payloads are valid, are taking them in, and they're actually validating those transactions, and they're moving the chain forward. And that is basically what it means for the merge, so to say. It's basically taking our execution layer as it was, and then combining it with the consensus layer of the beacon chain so that it's technically functioning as one chain. So yeah, this is again just another short note about the engine API. So basically how the execution client communicates with the consensus client, so to say. So we basically have an ETH2 client, which is basically running on the beacon chain. We have shard chains, which we do not have yet. And then you have like a specific beacon state, and then it has its own gossiping protocol. And on the other hand, you have an Ethereum layer 1 execution client, so to say, which is basically the actual execution, where the actual execution is happening using the preset rules of the EVM, and you have its own state trie, and then you get transactions from the mempool. And again, they're gossiping with their own clients, basically. So you have the ETH1 engine that is gossiping with the Ethereum execution gossip protocol, so to say, and then you have the consensus layer client that is gossiping with the consensus clients. And you have basically these RPCs to interact with each other. So basically, like let's say the Ethereum 1 engine wants to produce a block. They think that they'll just send over a payload to the consensus layer will validate it, order it, and then include it in consensus. And you have it back, like once a fork choice has been made, then you can kind of get it back from the consensus layer. The consensus layer is like, yeah, this block is asserted, we have produced this block, and then move forward with the chain. And that's basically a basic overview into how the engine API works. And yeah, so now we kind of come to the more important questions of data availability. Like I mentioned this word before on, and I think now is a good time to establish context into what exactly does data availability mean, and how does it fit into the modular blockchain infrastructure. So basically, data ability can be treated as the guarantee that the block producer actually published all the transaction data for a block and that the transaction data is available to other nodes. So basically, the way that it works in Ethereum is that for a transaction to be valid, the transaction data for it needs to be valid as well. So it basically means that the full nodes are out there verifying and re-executing those transactions with the data that has been provided by the block producer. So basically what it means is that the nodes in the consensus can then download the block data. They can then verify that the data is valid, and then it actually agrees to the transactions that have occurred. If this did not occur in Ethereum L1, so to say, it basically means that a block proposer could get away with inserting malicious transactions or invalid transactions, so to say. But basically we'll realize later on that how kind of this is a bottleneck for scalability. And the Ethereum L1 as it kind of currently is, it's basically having execution along with data ability on the same chain, which basically allows it to have like a clean ledger of transactions, which means that the transactions are verified and executed on the same chain so that they can always be treated as valid. And this is something we call as on-chain data availability. All right. So before we go on to the meaty parts of it, we can kind of delve into the blockchain trilemma a little bit, right? So basically, the blockchain trilemma is like kind of simple to explain, but basically you can kind of have three tenets that a blockchain seeks to have, which is decentralization, scalability, and security. And the way that it functionally is, or the way that the blockchain trilemma kind of claims to be, is that you can kind of only have two of these with a certain amount and not have the third. So if you take Ethereum as an example or Bitcoin as an example, right? These are basically the classic L1 chains which are responsible for settlement. And the cases of both of them is like they are highly secure and they're highly decentralized. So you have like a huge network of decentralized nodes and you have like a proper way of determining finality. But what they do not have is scalability. Because like let's say you have like 1,000 validators, right? Or let's say 2 million validators. At a certain point of time, you'll reach a bottleneck with the messaging overhead, and it won't be possible to scale the network as much. So there are different ways to kind of cope with this. You can kind of go into this multi-chain decentralized world, where basically the transactions are highly decentralized, where you have different nodes which are responsible for executing transactions. But what you do not have is the security. Like because it's a multi-chain world, the chances of the ways of determining finality is much more complicated. And finally, you have something like Hyperledger, Ripple, which basically have scalability and security, but they do not have decentralization. So it's basically like you either have a very limited amount of validator set, or it's basically not as distributed as a typical network like Bitcoin and Ethereum. So just to kind of explain in gist what those terms actually mean, you can kind of think of scalability as network throughput and network growth. So like let's say that a network were to scale from 1 million to 5 million users. How would the network scale? And like TPS, for example, like transactions per second, like how many transactions can a network process per second? That's a very basic metric of scalability, which is not exactly accurate, but it is a metric nonetheless. Secondly, you have decentralization. So for decentralization is basically like how distributed the network is and how easy it is for a centralized actor to influence the network. You can kind of think of it as like how many nodes are responsible for actually verifying the transactions on the chain, or how many validator nodes are validating the transactions on the chain. Like that is one way of thinking about it. And finally, you have security. What security technically means is how easy is it to mount an attack on the chain. So it's so like if you have like very less validators, it is theoretically much easier to mount an attack. If you have like a validator network where you have the minimum stake, or you don't have proper slashing implementations, what it basically means it's much more capital efficient to mount those attacks, which is again not the case for Ethereum or Bitcoin, because with Bitcoin you're fighting against other proof of work miners who probably have beefier hardware. In Ethereum you're probably fighting with like 10,000 other validators who have like 32 staked ETH each. So the way that Ethereum seeks to solve this is that the chain, in any case where there is a slashing event, there has to be someone who's losing 1/3 of their stake, which means that there is always the 2/3 majority to move on to the next attestation and so on. So basically, if you look at Ethereum L1 or the state of Ethereum L1 right now, it's basically, we can kind of treat them as sufficiently decentralized and sufficiently secure, but where we are not there is sufficiently scalable. Because if you look at the rate at which, for example, the Merkle Patricia trie or the entire storage state is growing, right? It's like around 100, 150 GB, so to say. And if you look at, if you assume that we'll have more users join, because technically, since this is an ever persistent state, every action is sort of like additive, which means that in a hypothetical scenario, 2 to 3 years down the line, you would need like much more beefier machines and much more faster SSDs or NVMEs to maintain the same state. And where we want to be is basically this ideal blockchain where basically we don't sacrifice on any of the tenets, where it is like maybe a bit less scalable, but you have a high amount of decentralization security. Because like when you're talking about Ethereum L1 chain, we kind of treat it off as a settlement layer basically. So which is why it is fine to sacrifice on scalability a little bit at the cost of having decentralization and security as paramount goals. And that's where you probably want to be. Again, like this is different from different chains. If you look into something like Polygon POS, or if you look into this something like Polygon Hermes, it's going to be much more different than the case for Ethereum L1. And so now we can kind of think about like what are the different parameters or what are the different ways we can scale. The primary of which is actually data bandwidth, which is basically like what is the maximum amount of data that you can fit into a block that can be safely produced within that allocated block time so that you don't miss the slot. You can kind of think of it in different ways, but this is like one way to think of it. You can kind of think of it as the number of transactions as well, but it's like the number of transactions don't matter as much as the amount of data that can be included in a particular block. Secondly, you have block times. Theoretically, like the smaller the block time, the more transactions you can accommodate. But with block times, you obviously have overheads of the more blocks you have, the more you're gossiping, the more amount of time it takes. Like there's a propagation overhead for each block that you produce. So basically, the question is like, what is the minimum amount of time that that is required before a block is produced? So basically, the transaction being picked for inclusion from the mempool, and then the transactions is actually being executed on the execution layer. And so obviously the bottleneck is the block propagation time. You produce the block, other nodes need to pick it up, they need to validate it, and they need to ensure that you're not being malicious. Third question would be of finality. Like what are the typical questions of probabilistic or non-probabilistic finality? So for a proof of work chain like the previous Ethereum L1 chain or Bitcoin, for example, you would have probabilistic finality, where basically the idea is that the more blocks that are being produced on top of the previous block, the idea is that it is technically impossible to reorg that block out because you would probably not have that much computational power to do so. This is kind of different for proof of stake chains, where you can kind of build these rules around block attestations, and you can have like instead of having it by difficulty, you can kind of implement like HLMD Ghost along with Casper FFG, which is responsible for determining like after one epoch, a block has to be treated as finalized or justified, and then after that block is justified, you can kind of treat that block as finalized. So obviously, the bottleneck here would be the number of validators. Since the more validators that you have, is more propagation is required to reach consensus. This is actually one of the typical reasons that on Ethereum Beacon chain, the minimum amount of stake that is required is 32 ETH. Because if it was very low stake, then you could kind of have more validators running, which would be more decentralized, but which means that you'd have an exponentially more gossiping to do to attain consensus. So by having a high minimum stake amount, you can cut down on the amount of validators that are validating on the chain, and you can kind of reduce the propagation overhead for the consensus messaging. And the last is obviously transaction throughput, which is basically how many transactions per second can this chain handle. Again, like we call this theoretical throughput because technically most chains are like something like EOS, for example, which can claim up to like 30,000, 40,000 transactions per second. Those don't translate into real world 36,000 or 30,000 numbers, right? And typically they also include state transactions. Like, so as, for example, it might include like consensus messaging like Solana.
it can include non-finalized transactions as well. Because we also talked about so-called finality in the previous point, there is no guarantee that the particular transaction throughput also ensures and includes finalized transactions in that particular measure, so to say. And so these are kind of the different scaling vectors that you can seek to solve using modular blockchain. So the first scaling solution that I think we have all heard of and we can talk about is optimistic rollups. So something like Arbitrum, something like Optimism. You can kind of think of them as a scaling strategy that is based on side chains, where you basically have someone responsible for transferring assets. You have a contract on the L1 chain, you deposit the assets, you get it on the other chain, and vice versa. And they basically have their own dedicated block producers, right? This is what is, so basically when you spoke about splitting of the execution layer before, this is sort of what optimistic rollups are mainly trying to do. They are trying to remove the execution from the L1 chain onto the particular optimistic rollup. And the rollup operators themselves can then batch those transactions in, and then they will publish them on the Ethereum chain along with the call data. You can kind of apply different heuristics to it. You can kind of do call data compression. You can do all of these. Arbitrum Nitro, for example, they're trying to do something more interesting. And then you post on the Ethereum chain. But so basically, the block producers can still misbehave and make blocks that produce invalid transactions, right? And in which case is basically where fraud proofs come in. So you can kind of submit a fraud proof, which proves that a state transition that has been committed on L1 is technically invalid. And this basically means that the batches submitted by that particular operator would be kind of removed. And then the idea of that is what basically the word optimistic and optimistic rollups means. It is basically the batch is treated to be valid until it is proved with a fraud proof that is not valid. And which is why they require this time period, or what's called a fraud proof time window, where basically for Optimism, for example, it's like 7 days. So basically, you cannot withdraw until those 7 days because you are relying on the security assumption that within those 7 days, if a state transition were to be invalid, someone would submit a fraud proof for that and revert the particular state transition. And yeah, so this is where we again have a question of data availability. Since the way that it works is, like if after the particular time period window, you want to assert that that transaction has actually been included and the transaction is actually valid, for which you need data availability. So if you want to construct the proof for that particular data, you would need some way to get those transaction data from either a DA layer or from Ethereum L1 to ensure that there are no invalid transactions that are detected. We'll talk a bit about ZK rollup, so to say. Yeah, go on.
About the optimistic rollups.
Yeah.
Like, how are the transactions verified? Because I think now on the optimism one, like the fraud proofs are disabled.
Yes, they are.
And it's kind of centralized right now.
Yes, it is. So that is a very big flaw of some optimistic rollups, like Optimism, for example. Like they do have good work coming out, for example, like transaction call data compression and all, which is great. But without fraud proofs, it is technically a sidechain. It is no longer an optimistic rollup, so to say. Like the optimistic rollup, a very, very basic necessity for an optimistic rollup we call an optimistic rollup is that it must have the ability for anyone to submit fraud proofs within that particular time period so that it can revert the state transition function. So the assumption in the case of something like Optimism is that you are assuming that the transaction data that is going to be submitted on Ethereum L1 is always correct. So it's basically you're trusting the majority of the rollup operators on the chain to assert that they are not lying. And this is what ZK rollup seeks to solve. So basically, with ZK rollups, you no longer have the requirement to submit fraud proofs to prove invalid state transitions, but instead what you are submitting is validity proofs. So you submit a validity proof that basically asserts using ZK cryptography that the state transition from S to S0 is valid. And once that valid proof is submitted, then you can kind of assert by using the math alone that the state transition that has occurred or submitted by the particular rollup operator is valid. So it removes the requirement of an external actor having to provide a fraud proof to disprove that the transaction is invalid. And validity proofs themselves do not require proof availability. data availability because technically it's just a proof of the state transition function. So basically all you're proving is that the state transaction is valid. But they do require DA, as we'll talk about later on. And so we finally come to what we call the DA problem. So how do you verify that the data is available for a newly produced block? If a block producer doesn't release all of the data in a block, then theoretically no one could detect that there is a malicious transaction hidden within the block. And the way that Ethereum seeks to solve this is by having all block producers publish the entire transaction data in the networking layer. So basically all other validator nodes can then assert, all other full nodes can assert that the data that has been published and the block that has been produced are conformant with each other. And this is the scaling problem that we talk about. And in optimistic rollups, we spoke about how we kind of need to publish the entire transaction data on the chain, because if you didn't do that, then technically you wouldn't be able to construct those fraud proofs to revert that invalid state transition, which theoretically means that if in a scenario an OR was not doing that, then you would not be able to revert the state transition function anyhow. And finally, we have ZK rollups. ZK rollups sort of need to store the transaction data on chain as well, because validity proofs only verify the authenticity of the state transition and nothing else. So let's say you wanted to withdraw your particular money from ZK Sync or something like Polygon Hermes. You would still need to provide a proof of that particular transaction having taken place. So typically the way that it works is you have some sort of a Merkle tree. You construct a Merkle proof of transactions, and then you submit the proof along with your particular transaction that you want to be executed or communicated back to L1, and then that is executed back on L1. Without access to transaction data, what it basically means is you cannot query your account balance, you cannot initiate transactions that rely on the state information. And which is why ZK rollups is basically, and we'll talk about how we can kind of scale ZK rollups as well. But yeah, like that's basically how ZK rollups work. The data availability has to be on Ethereum for it to be called a ZK rollup. All right, this is a basic attack vector, so to say. Let's call it the fisherman attack for brevity, right? Where basically you can kind of have this case where someone is not publishing their block data, and you have a full node that is responsible for like ringing the alarm, which is called the fisherman. So theoretically, what can happen is they do not publish the missing data, the fisherman raises the alarm, and immediately the block producer releases the data. And then you have another case where they publish with all the data, and then you have the fisherman which raises a false alarm. So basically what it means is, in the case that you have a positive reward mechanism where you are rewarding the fisherman for raising the alarm, they are always incentivized to raise alarms. And theoretically, they can collude with a block producer such that they can get rewards. In the scenario that you didn't have any rewards, where basically you would not lose anything by doing that, then in that scenario, what they would do is they could do the false alarm with every block that is being produced, which basically would mean that every other node would listen to that false alarm. They'd have to re-download all of that transaction data, and it would kind of negate the entire point of scaling in the first place. Like it would nullify the benefit of light clients or sharding. And lastly, you have a negative sum game, right? Which is basically like you are disincentivized from ringing the alarm, so to say. In which case, there basically there can only be altruistic fishermen, which basically means that only the people who actually want to ensure that the network is running fine, only they would be the ones responsible for raising the alarm. And in that case, what would basically mean is since they can just wait for their capital to be exhausted, the fisherman's capital to be exhausted, and after that amount of time, they're free. They can continue with their data unavailability attacks unimpeded. This is again just a very basic case. Sorry if I'm getting too technical into this, but yeah, feel free to ask me any questions. So basically, the solution is then to have varying trade-offs as to how we kind of implement this. Like for example, optimistic rollups deal with this by posting the entire transaction data on chain on Ethereum. ZK rollups kind of trade the infinite scalability of something like Plasma, where data availability is off chain, by publishing some transaction data on L1. But what this basically means is that the scalability of rollups is limited by the data bandwidth and the transaction throughput of L1. And with this data availability reliability on Ethereum, the only kind of scaling that you can kind of sort of do is horizontal scaling. And the main way that Ethereum wants to scale going forward is basically sharding. And so we'll talk about sharding more about in the kind of the Ethereum roadmap, so to say. And yeah, so basically the point that I want to convey kind of through this talk is not that Ethereum is bad or that monolithic blockchains are bad. Is the fact that monolithic blockchains do work. It's just that modular blockchains are better. And we'll talk about that in just a minute. And so basically this is where we introduce the topic of off-chain data availability. So we already know that like the on-chain data availability kind of places bottlenecks on scalability, since we kind of need the entire transaction data to be on the chain, which means that they are kind of slower because they must re-download and verify the same transactions again and again, and requires node to store increasing amounts of memory, increasing amounts of state, which would affect decentralization, because you would need beefier machines. It would get more expensive to run validator nodes, and it would disincentivize people from running their own validator nodes, because how expensive it would be to run those. And so this is where we talk about off-chain data availability, because what we can basically do is we can move the data availability layer to another chain completely. So basically the block producers don't have to publish the transaction data on the chain, but they can kind of provide a cryptographic commitment to prove the ability of the data. So you have the idea of, for example, Polygon Avail has KZG commitments. And typically it's like these are all implementations of eraser coding, which is basically like you can commit a larger batch of data, so to say, which you can kind of sample using DAS and so on and so forth. And so basically this is the method that is used by the modular blockchains, where some chains can manage some tasks and the rest of it is offboarded to other chains. So you can have, for example, transaction execution on one layer, you can have consensus on a different layer, and then you can have data availability on a different layer, like Polygon Avail. And finally, we come to another class of scaling solution called validiums. It's basically, you can kind of think of them as ZK rollups, but the data availability for validiums is basically done off-chain. So basically, same like ZKR, they publish the ZK proofs of, to verify off-chain transaction on Ethereum. This allows the invalid state transitions to occur because it has a high level of security guarantees as well. And basically the funds that are belonging to a particular validium are all controlled by the same smart contract Ethereum. Once the validity proof is submitted, you can submit the Merkle proof for your particular transaction, and then you can assert that this particular transaction actually taken place, which allows the on-chain contract to process the withdrawal. But yeah, like therein kind of lies the crux, that basically users of a validium can kind of have their funds frozen if the data availability managers kind of withhold the off-chain state data, which basically means that because since you do not have access to that transaction data, the users cannot compute the proof required to process their withdrawal, to prove ownership of funds or to execute withdrawals. And this is the major difference between validiums and ZK rollups, where one of them will have the data availability on L1, and the other of them will have data availability on a different layer, so to say, or in itself. So we kind of introduce the concept of eager versus lazy blockchains, where basically we have an eager blockchain protocol such as Bitcoin and Ethereum, which kind of combine transaction execution and verification on the same layer with consensus to ensure that only valid transactions are included in the ledger. In contrast, you can have a lazy blockchain, which basically separates the consensus layer or the DA layer, which is responsible for ordering the transactions, from the execution layer, which is responsible for verifying them. Where basically you can have these dirty ledgers where basically like the transactions are meant to be processed downstream by the other entities like full nodes or validator nodes. So just to intro sovereign rollups, you can kind of think of them as ZK rollups where DA is off-chain and they do not have sort of any interaction with Ethereum or L1. So if you recall, validiums can still do settlement on L1. Sovereign rollups kind of tend to take that out entirely, where it is a rollup by itself and it interacts with only a DA layer such as Polygon Avail. And then you also have the idea of a lazy blockchain. We spoke about how it doesn't do transaction verification. It only guarantees the ordering and the data availability of the transactions. And so basically the main idea, or basically the main reasoning of why sovereign rollups are a good idea, because you can kind of theoretically build this rollup where the end user, which is you, can kind of verify cheaply and trustlessly with a lightweight light client that a transaction is valid. And you can kind of do this on your mobile, because since you're offloading most of the data availability and consensus to probably other chains, it allows for a light client to sync as with much lesser computational power. And so the general thinking on rollups that you need to kind of rely on Ethereum security, for which again you need to pay an expensive cost. We can kind of reduce the cost that needs to be paid. We can reduce the computational power by enabling the idea of sovereign rollups, which basically we kind of invert the model to this end user driven model which is scalable with time. And if you kind of look at the distributing processing models of something like AWS, GCP, that's kind of basically how it works. You pay for what you use, and it is much cheaper and effective to use those. And so that we come to the last slide of content, I think. So basically where we are at right now is we have just merged. Eventually we'll have withdrawals, we'll have sharding, we'll have collier expansion, data availability sampling, Merkle trees. We'll remove the Merkle per tree share trie, which allows for scaling with statelessness. We have history expiry, which is like a one-time history expiry, which allows for a reset of the chain. We'll have state expiry, which is like a rolling expiry of the state, such that the state cannot grow to an indefinite amount. And then finally, we have proposer builder separation and verifiable delay function. These are probably very far off. We are probably the closest to the surge right now. But again, these are probably questions for another day. So yeah, just wanted to thank everyone who made this talk possible. A lot of this content was sourced from ETH Research, Ethereum.org, Ethereum Magicians.org, Vitalik himself, Anurag, who is the co-founder of Polygon, Paulinia, who is again this great person with modular blockchain thesis. That is Mustafa, who is the co-founder of Celestia, Prabal, who works at Avail, leads Avail at Polygon, and Manav, who leads POS at Polygon. So yeah, I think we are in good hands. I think there are people in the ecosystem who are building towards some great things. So yeah, I think we are on the correct path. And that's pretty much it. I hope you guys liked it. If you guys want to hit me up, there's my Twitter, there's my email. But yeah, that's it. And thanks a lot to the organizers and all of you for listening.
So we do have time for just a few questions, then we have to set up for the remote talks. So would anyone like to ask a question?
Go for it. I'm listening.
All right. Okay. Well, thanks again.
Likewise, great to be here, guys.